for long enough so that we see the momentum distribution, we take an image, and then we can fit that momentum distribution to the answer to this integral, which is the integral for the momentum distribution. Okay? And what we do is we leave as free parameters in that fit the temperature, T, and the fugacity, which is another way of just talking about the chemical potential. All right? So we'll take an image. This is an example of image. Actually, this is a famous image. This is one of the first Fermi gases anybody ever made. That's what I did for my graduate work, and I sneak that into all of my talks. And I can take an angular average of this and show you a radial plot of this density measured as an optical depth. And this axis is like radius. You should think of this axis as momentum. Sorry, that got cut off there. And you can see the kind of distributions we observe as we lower the temperature from about TF down to about 0.2 of TF. And we can fit that. There's a fit there. And that fit allows us to determine the temperature and the fugacity, which is another free parameter. And this is data taken from a whole bunch of different gases, cooled to lower and lower temperatures. And this is a measured fugacity from fitting to this distribution. So that's how we find out all the thermodynamics. We measure what's happening in a gas. But this requires a solution to the problem. Okay, but for a weakly interacting or an ideal Fermi gas, we know a solution because we can do these intervals. Okay, does that make sense, how we do this? This is kind of important because I think this is a point which, for people from different areas, is often misunderstood or missed or doesn't make sense. Okay? All right, in this system, I mean, this gas, which we did these measurements on, like this gas or any one of these points, right? So one of these points here, T over TF about 0.2, it's probably about this one right here. That's taken from an image. This image, here's a radial distribution, that's that point. That has a well-defined number of atoms. There's a certain number of atoms, right? And a certain amount of energy in that. Okay, and that's why it has a well-defined chemical potential of fugacity and temperature. Right? Those are conserved things in this system which is closed. Make sense? Yeah?
So when you're measuring the momentum distribution,
yeah.
That's a destructive method, right?
Yep.
So how many times roughly did you have to do that plot in the left?
That, one of those points there is one measurement.
Okay.
Yep. There's no averaging of that. Yep. Yeah, that is the trick to doing these experiments well. Things have to be very reproducible. There's like, I don't know, one of our experiments now has, I think, 17 lasers in it and a bunch of other stuff, right? It's complicated experiments.
Is this something that you could repeat for anything that you could just do enough times and was computationally feasible enough to do this kind of fitting?
I'm not sure what you're asking.
Like this particular works for ideal fermions, but you say, okay, we're getting the temperature by doing something that we can then fit against the temperature. So anything that we could fit against the temperature that we understand the physics well enough.
We have to know the physics. So for example, I'm not going to talk a whole lot about it in these lectures. I will a little bit, but we also do experiments with these optical lattices where we realize Hubbard models.
Yeah.
Right? Generally we don't have solutions, right?
Yeah.
And so that's a problem. We actually don't know how to measure temperature.
Could you try to couple it to something else that you understand?
Yeah, my group and other groups have tried to do that, and I'll talk a little bit about using spin-dependent lattices, I think maybe tomorrow, or my second lecture, where we try to introduce an impurity. But unfortunately, that also may involve physics we don't totally understand, as we discovered. And in fact, in those experiments, what we discovered is, in my group, an analog to Kapitsa resistance, where that impurity doesn't thermalize very well at low temperature, so that's another problem.
Fair enough.
Yeah. Okay, so let me keep going. Okay, so let me give you another example of thermodynamics to help you sharpen your thinking about what happens here. So let me talk about something we do very commonly in experiments, which is we have this trapped gas and I superimpose a periodic potential on an optical lattice. What I do is I slowly turn that on, attempting to be adiabatic while I do that. Okay, so I can ask myself a question, and that question is, what's the new temperature now? And if these particles are ideal or weakly interacting, I'll talk about the ideal case, I can do that. I can find out the temperature after they turn on. And what physics do I have to do to think about that? Well, let's see how this is cut off or not. Okay. You know what? You probably figure out what I wrote here. What you're really doing when you turn on this optical lattice is you're going from a parabolic dispersion for the free particles to something like a tight binding dispersion for the particles once the lattice potential is present. Okay? So that's 2t 1 minus cos pi q over qb. QB is the edge of the Viron zone there. All right, so I'm changing the dispersion. I'm trying to do it adiabatically. How do I think about what the new temperature is? Well, I do some thermodynamics, and this is not working. I think I know why. Okay, so what I do is entropy matching, and this is a commonly used technique which is what I want to talk about to understand what is that temperature I've got. So what I can do is I can say, okay, I know what the number of atoms is. Here's the integral for the number of atoms. And after I turn that parabolic potential on, I've got my trap still, but now I've got a tight binding dispersion. Okay, so I plug that in for h into that integral. Okay, and I also can write down integrals for the entropy, right? I can write down the integral for the thermodynamic potential. If you like to think that way, you pick the way you want to think. I can write down an integral for the entropy, and the entropy is just the derivative of that thermodynamic potential with respect to temperature. Okay, so these integrals now are equations which together tell me what the new chemical potential and temperature are. So what I do is I know after I've turned that lattice, the number of atoms hasn't changed. I know the entropy of particle hasn't changed. And so I can put these two equations together. I can solve them simultaneously to determine the new chemical potential and new temperature in that optical lattice. And here's an example from a calculation Blakey and Porto did. So along this axis is the lattice potential depth. And here's the entropy. And these are curves that show you, sorry, this is the temperature along this axis. This is the entropy per particle. And these are curves from no lattice up to strong lattices. And you can see by following an isentropic curve here, you can figure out how the temperature changes. For example, if I start at low enough temperature, the gas cools enormously as I turn the lattice on because the dispersion is flattened and all the energy scales have dropped. On the other hand, actually, the gas can also heat if I start at high enough temperature, entropy per particle, as I turn on the lattice. So that's a way to think about thermodynamics in this system. One commonly used tool to predict what's going to happen is this entropy matching technique. Okay? Does that make sense? All right. Okay, so the thing I want to talk about now is how do we do things with these atoms? How do we manipulate them with light? Trap them, manipulate them, do stuff with them. We pretty much always shoot laser beams at them. And the reason we shoot laser beams at them is because the laser beam has an electric field, and the electric field couples the electric dipole moment of the atom. It's got that electron, that valence electron sitting out there. That valence electron can form a strong electric dipole moment. We can induce it with the electric field and yank that electron around, which yanks the whole atom around. And so that's how we manipulate these atoms and do things to them. And one thing let me just say is that often you'll read in papers or people will talk about this as if these potentials are perfectly conservative. They're not perfectly conservative, and the reason for that is that there's always a little bit of spontaneous emission, because anytime you turn the light on to manipulate these atoms, there's a little bit of quantum amplitude up in the electronic excited state, which can decay. And that will lead to heating and momentum diffusion. So sometimes that effect is weaker or stronger, and this is something which spoils the system from being completely closed. But there's some time scale over which there's just, the probability of spontaneous emission per atom is very, very small, and we'll treat the system as being approximately closed. But this light scattering is always happening, always leading to momentum diffusion and some amount of heating once we turn on some light to trap and manipulate the atoms. Okay, so how does this work? How do we make optical potentials, optical lattice, optical trap, things like that? Well, here's my atom. It's got a ground electronic state and an electronic excited state separated by some optical wavelength. For many of the alkali atoms, this is in the range of 600 to 800 nanometers. And when I turn on some light with an electric field, that atom forms an electric dipole moment that just interacts with that electric field. It's really an induced electric dipole moment, induced by the electric field, which then interacts with that electric field. Okay, so there's the interaction Hamiltonian. And here I'm ignoring momentum. Really, of course, this light has momentum as well. Sure, it'll be omega laser, or kx minus omega laser t, but I'm going to ignore the momentum here for the time being. All right, so we turn on the light, induces electric dipole moment, which now that induced dipole moment interacts with that light. Okay, so here are some basic definitions from AMO physics. In this two-level approximation, and in the electric dipole approximation, we can write down the matrix element for that interaction, and we call that matrix element with the correct prefactors here, the charge and the electric field divided by 2. Call that the Rabi frequency, capital omega. And then with the, oh man, I'm going to forget even what I've left off the bottom of the slides. All right. And then what we call the rotating wave approximation, which is appropriate when, for example, that Rabi rate is much smaller than the detuning of that electric field from this natural resonance, right? The laser frequency can be different than that natural resonance. So there's some detuning, which is the difference of those two. What happens is the the states shift, okay? Because that light mixes some of the excited and ground states together. So we have these excited state or ground state. When we turn the light on, they shift. For example, I've drawn it here as if the detuning is negative, and this state shifts down by an amount h bar Rabi frequency squared divided by the detuning. Okay? That's called the AC Stark effect, or the AC Stark shift, or the dipole shift, or people use lots of different words to do this, talk about this. And one thing you'll notice is that Rabi frequency squared is proportional to the electric field squared, which means that energy shift from the light is proportional to the intensity of the light. Okay, so the atoms experience a potential shift, which is dependent on the intensity of the light. That means we can exert forces on them by having intensity gradients present. Right? Actually, just as an aside, one thing actually people just sort of forget about, where this detuning effect comes from really is that, you're inducing a dipole moment, and that dipole moment is oscillating at the laser frequency. And so that leads to an oscillation which is in phase or out of phase of this resonance. And so that leads to either an energy shift, which is positive or negative, is that electric dipole that you've induced leads or lags the electric field. So that's why there's that detuning dependence there in a sort of simplest lowbrow point of view. Okay, and depending on where you set your laser frequency, this energy shift for the ground state, which is really the state we're working in, can be negative, the detuning is negative, or positive, the detuning is positive, that state can shift up. Okay, so this does not show up fantastically well. Actually, that two-level approximation is poor for all atoms anybody works with. This is what a real atom looks like. This is rubidium-87. Here are the two hyperfine ground states, the states we use to do experiments in. So there's F equals 2, F equals 1. That means there's MF equals 1, 0, minus 1, and 2, minus 1, 0. Sorry, 2, 1, 0, minus 1, minus 2. Those are the states we use. There's actually two transitions, which are not too far detuned from them. There's a so-called D2 transition to the 5p3 half state at 780 nanometers, and a D1 transition at 795 nanometers. And people do tricky things with all, including my group and many other groups, with the fact that this is not just a simple two-level atom. And so the real dipole potential, or AC Stark shift, if you write it down for a real alkali atom, actually looks like this, where you've got a dipole shift or potential shift proportional to the intensity of the light. That comes from the Rabi frequency squared. But the internal structure of the atoms leads to more complicated dependence. It leads to dependence on the polarization of the light, that's P, the MF state, and actually still the detuning comes through, but there's two resonances here that you need to pay attention to, and each resonance contributes to the dipole shift. Okay, so there's a reason I'm telling you about this and why this is more complicated, and that there's a polarization dependence and an MF dependence here. I'll come back to that later today when I talk about making an impurity disorder in these experiments. Okay, net gamma, that's proportional to 1 over the excited state line width, and that's a measure of how well the electric dipole couples the electromagnetic vacuum. And it's typically 2 pi times 6 megahertz for most of these alkali atoms. Okay, so that's what a real atom looks like, and I'll come back to that later. Yeah?
So when you assume the Rabi frequency to be very large compared to the detuning, then your dipole frequency becomes this.
No, so these equations are only true when the Rabi frequency is small compared to the detuning.
Sorry. So I just wanted to know, what do you exactly mean by rotating wave approximation? How does that? So we started with this E dot R.
Yeah.
And then.
So so the rotating wave. Let's not get into that in these lectures. I will afterwards point you towards good books where you can read about this. It's really not important for these purposes. I will write down, there's a correction to the rotating wave approximation that needs to be made for these formulas, and I'll show you what that is. But you should just take these formulas as some atomic physics magic that happens, and these are the potentials which are created.
One more question.
Yeah.
What is this I of R?
Thank you for asking that, it's very important. That's the intensity of the laser beam.
So is that an operator?
No, that's the intensity of the laser beam. Actually, great question. So a lot of people don't appreciate this either, but laser beams, to a very good approximation, are a coherent state of light. And a guy named Mallow proved in 1978 or 1979 that a coherent state of light, when it interacts with an atom, acts as if it's a classical field. So this, what I wrote down here is really the atom. That R should be an operator, actually. That's the R for the electron. That should be an operator. That E is really a classical field. To a very good approximation, just treat it as a classical field. It has an intensity, right? proportional to E squared. And that intensity is really important. I'll show you how that intensity comes in. But that dipole potential, or Stark shift, things people use different words to describe it, it's proportional to laser intensity. And that's maybe the most important thing you need to take away from this.
So there is no operator in this whole expression?
No, this is a potential energy. It's basically classical. All the operators, so when you write this down, this R should actually be an operator. It's the R for the electron, but this field is classical. We do a bunch of math, a bunch of atomic physics, and you end up with this, and it's like a classical potential term. Okay? Thanks for asking that question. Okay. So let me give you some examples of how this works, examples which are important, which I'll come back to several times, especially later today. So how does this work out? For example, how does this let us trap an atom with a focused laser beam? That's what we do all the time in my group and many other groups. Well, if you take the limit of that equation for a two-level system for a large detuning, here's that dipole potential. If that detuning is large compared to, so for example, there's this fine structure here. If that detuning is really big, let's say I use a 1064 nanometer laser. So the detuning is very large compared to this fine structure, and it's very big compared to the natural resonance. Sorry, it's I went big in that direction, but 1064 nanometers is actually a much smaller energy. Then I can write that potential down in an easier form. All right, it's got that excited state line width in it, which is proportional to 1 over the excited state lifetime, which is about 30 nanoseconds. That's about 2 pi times 6 megahertz. It's got the detuning of the laser beam in the denominator and the intensity of the light that it's proportional to. Okay, so this is the important thing that I want you to think about a little bit, and why I'm going to give you some examples. So for example, if I take a laser beam, and here's my laser beam. Laser beams you make with lasers have Gaussian intensity profiles characterized by a waist, W naught. And I'm going to tell you a lot about optical speckle later because no one ever does this, and I thought it was a good chance to do it. This idea of a waist is important, so that's the waist of the Gaussian laser beam. We send through a lens that has a focal length. It focuses it to a Gaussian spot, all right, with a smaller waist, W naught prime. All right? And the beam is propagating along the z-axis. This is how you focus a Gaussian laser beam. All right, and a Gaussian laser beam, this is a definition of the waist and what the intensity profile of that looks like. And so because the intensity profile near this waist here is Gaussian, it means you'll form a Gaussian potential for the atoms. All right, and here's a bunch of math, which you can come back to later for how Gaussian beams focus. This is kind of important because if you want to deal with and understand these experiments, you need to know how we do certain things. And so, what controls the size of this focus is the wavelength of the light and the focal length of the lens. If you use a shorter focal length lens, you get a smaller focus here. If you use shorter wavelength light, you get a smaller focus and a tighter trap. ZR is called the radial length of a laser beam. It's also controlled by the waist, the size of the laser beam, and the wavelength of the light. So if you think about what kind of potential you're going to get here, if the detuning is negative, like I use a 1064 nanometer laser beam, then this is an attractive Gaussian potential that will trap the atoms. And that's what a dipole trap is. That's how we trap atoms with a laser beam. We do that all the time. We might focus a laser beam. Let's say this waist might be 100 microns in my group. Does that make sense? It's the most basic tool. And I want to tell you how we make disorder in these experiments. We're going to talk about something much more complicated than this. So if you don't understand this now, just please ask questions. You don't know what these terms are or what I mean when I'm talking about this. Okay. So that's a focused Gaussian laser beam. We can also do things like often we take 2 laser beams and cross them. Like we might have another one coming in and out of the board here. And I'll make a nice sort of spherical looking trap within the kind of 100 micron radius of the beams. That at low energies, when the atoms only sample the bottom of that Gaussian potential, will look kind of parabolic.
Sorry,
Yeah.
Localized, when you say localized, it's only localized in the x-line, right?
No, actually this, if you look at this formula here, in fact, because as you move along the axis, the intensity is getting bigger, this actually traps atoms in 3 dimensions. Right? There's a potential minimum here in all dimensions. Right? Because, think about this formula for a minute. As they go away from the focal plane here, the intensity drops. Okay? Right? So that means that there's a potential minimum in all directions. No matter which way I go away from this center point here, the intensity drops. So that forms a trap. Right, along this direction, it's kind of weak for a single laser beam. And maybe you make a 1D gas this way by taking one laser beam and focusing it, which is why I showed you this, because I'll talk about 1D disorder later. So for example, I can make a 1D gas here, be very elongated